Welcome to Lecture 17 for Radiochemistry 312. This lecture is on radiochemical separations, and it's in 4 parts. The reading for the separation lecture is Actinide Separation Science and Technology from the Chemistry of the Actinides and Transactinides. The separations lecture will cover solvent extraction, ion exchange, separation methods you should be familiar with. We'll also explore electrochemical-based separation, where the redox of the metal ion that's undergoing separation is changed, either to an oxide state or a metallic state. Reduction and oxidation can both be used. And we'll also explore volatility-based separations, where the target radionuclide is separated by forming a volatile species. The 4th part of this lecture will review specific actinide separations from neptunium, plutonium, americium, and curium. And these are reviews from previous lectures. Part 1 is going to focus on solvent extraction, and primarily the PUREX process, the plutonium-uranium extraction process. This is the workhorse of the nuclear industry, where plutonium, uranium separated from the fission products, and they're separated from each other. We will explore this in detail because it is one of the more important separations that are involved for radionuclides. To start, we'll review basic concepts involved in separations. One of the easiest ways to achieve a separation of a radionuclide from other elements is by varying the oxidation state. This is one of the benefits of the actinides, where we've explored that many actinides have various oxidation states. By tuning the oxidation states, having them separate from the metal ions that one wishes to separate them from, separations can be achieved. For instance, in the PUREX process, we'll see that the +4 and +6 oxidation states are extracted into an organic phase. The +3, +2, +1 oxidation states, +5 oxidation states remain in an aqueous phase. So by selecting plutonium and uranium as a +4, +6 oxidation state, they can be separated from other oxidation states. The uranium and plutonium are extracted. And then by varying the oxidation state of the plutonium from the 4 to the 3, separation from uranium is achieved. If oxidation state separation is not achievable, for instance, trivalent lanthanides from trivalent actinides, the ionic radius variation can be used as a means for separation. Also, between the actinides and the lanthanides, the role of the 5F electron can be exploited for separation of elements with the same oxidation state. So some of these advances, particularly with trivalent actinides, have been focal areas for the nuclear fuel cycle, with much effort involved in separating trivalent lanthanides from trivalent actinides. One of the reasons for that has to do with the nuclear properties. The whole concept of performing these separations is driven by the nuclear properties of the material in the used fuel. Very similar to the separation and understanding of uranium chemistry was driven by the nuclear properties of their isotopes. In nuclear fuel, one starts with uranium, produces actinides, higher actinides through neutron capture, and then the fission of uranium produces fission products. Those fission products can go from about 1/3 of the periodic table, from selenium to dysprosium. So this is a rich chemical environment. The idea of doing the separation is really driven by nuclear properties. If one wants to reuse the nuclear material for fuel in other reactors, one should remove fission products that have large neutron capture cross-sections, or separate the actinides from the lanthanides so the actinides can be reintroduced into the fuel, providing energy through their fission and also mitigating their disposal. Fission products need to be removed because they absorb neutron. In particular, there are some lanthanides with very large neutron capture cross-sections that, if left in fuel, will absorb neutrons, as opposed to having the neutrons fission the actinides. That'll reduce the efficiency of the reactor. That's one of the driving forces in the effort to separate the trivalent lanthanides from the trivalent actinides. One would like to keep curium, americium in fuel. One would like to remove the lanthanides. So we'll begin the lecture on separations, focusing in on the PUREX process. The main ligand in the PUREX process is shown here, tributyl phosphate. Coordination occurs through this oxygen on the phosphate. And above is shown a crystal structure of uranium with triethyl phosphate. Triethyl phosphate was used in this crystal structure because it's easier to crystallize than the tributyl phosphate. However, the coordination environment around the uranium, as we see that there's the EL oxygens, there's 2 nitrates coordinating, and 2 triethyl phosphates. Those, in the PUREX process, those 2 triethyl phosphates would be replaced by 2 tributyl phosphates. We see the 2 nitrates coordinating around the uranium, providing neutral charge environment for the uranyl. Uranyl, if you remember, is +2. Each nitrate is -1. So this neutral species can then be extracted into the organic phase. We also mentioned that plutonium-4, or tetravalence, can be extracted into the organic phase. The difference being that the coordination number of nitrates would be 4 as opposed to 2, providing a neutral environment around the metal ion. The fundamental concepts for solvent extraction is provided here, where we have 2 phases that are mixed and then allowed to separate. Example, again, using the PUREX process, we have tributyl phosphate, TBP, 30%, and kerosene mixed with a solution of nitrates of uranium, plutonium, fission products in nitric acid. These are mixed. After the mixing stops, the phases separate, where the organic phase is lighter, goes to the top, the aqueous phase is heavier, goes to the bottom, and from here the phases can be separated. The aqueous phase is contacted with the organic phasing ligand, so in order for a metal ion to be extracted from the aqueous phase to the organic phase, a neutral species needs to be formed. And if you remember on the previous page, we had 2 nitrates with the uranyl, so that would form a neutral species, and that drives the solubility in the organic phase. So the organic phase contains the target radionuclides. It may have other metal ions that are present. These may need to be further separated. So in a process, you may have a washing phase, and we'll talk about that. Of course, you can also do some other variations of the metal ions speciation later. You can change the redox state, or you can change the acid concentration to back extract a metal ion from the inorganic phase to an aqueous phase. And this is done in the PUREX process for plutonium, where plutonium-4 and uranium-6 are extracted into the organic phase. The plutonium is then reduced, and the trivalent metal ions are soluble in the aqueous phase under the extraction conditions of the PUREX process. So in that case, one can separate uranium and plutonium from most of the fission products and other actinides, separate the uranium plutonium into an organic phase, then reduce the plutonium from the tetravalent to trivalent state, and it'll go into an aqueous phase. And we'll describe that in a little bit more detail. And what one tends to measure is the distribution of a metal ion between an organic and an aqueous phase. You can measure this and evaluate that term as a function of chemical conditions. And this is simply, it can be done by measuring a concentration in an organic phase and a concentration in the aqueous phase, or knowing the total amount that was initially put in, measuring concentration in one phase and doing a mass balance in another. You can get a distribution coefficient. The higher the distribution coefficient, the more likely you'll find metal ion in the organic phase. And here's an example of where the mixing occurs. At this point, the 2 phases are mixed, and this allows the chemistry to occur. So within solvent extraction processes, the ability to mix phases is important, and as we'll see within industrial-based PUREX process, there's a number of different routes that one could use for mixing the aqueous and organic phase. Then again, once the separation has occurred, the organic phase receives the target radionuclides. The aqueous phase is usually sent to waste. For solvent extraction, we can vary solvent conditions. for instance, changing the concentration of tributyl phosphate in kerosene. We could also vary the ligand. We could have other ligands in the system. We can have two ligands for a synergistic type extraction. Or the aqueous phase can be varied. This can include changing the acid concentration, influence the metal ion. We've already discussed oxidation states. One can also add other counter anions, such as using a nitrate salt to increase the nitrate concentration. Variation of the concentrations can also result in phase splitting. This is usually called third phase formation. We'll discuss this at the end of this lecture. And third phase formation is when the organic phase splits into two, where you would have a ligand-rich, metal-rich organic phase and a ligand-poor, metal-poor organic phase. So you fundamentally have three phases in the system. As we discussed earlier, primary route of measuring the effectiveness of a separation or an extraction by solvent extraction is the distribution coefficient, which is shown here. It's just the concentration of metal in the organic phase divided by the concentration of the metal in the aqueous phase. An example of a distribution coefficient is shown here for uranium, where in 4.8 volume percent tributyl phosphate in kerosene, we see the distribution coefficient vary, increase as it reaches around 5-6 molar nitric acid, and then to begin to decrease. So what we see here, we see the formation of preferential extraction conditions, and under these conditions, the competition with nitric acid for the tributyl phosphate, this starts to displace the uranium, so the distribution coefficient decreases. Now if one looks at the distribution coefficient term, concentration of metal in the organic phase divided by concentration of metal in the aqueous phase, we see that if we're at 1, 50-50 mixture, so 50% of the metal ion winds up going to the organic phase. Obviously, if one wants to effectively remove the target metal ion from the aqueous phase or the organic phase, you'd want distribution coefficient somewhere between 10, which is around 90%, and 100, which is around 99% of the metal going into the organic phase. One can also use distribution coefficients in these systems to determine the stoichiometry of the extracted species. One can evaluate a parameter and look at the change of the log KD versus the log of that parameter. The slope is the stoichiometry. And again, this can be used to understand the speciation of the extracted systems. As we said on the previous slide, one could use the distribution coefficient to determine the stoichiometry of a system. Consider a reaction where we have so much X metal plus Y ligand going to metal X ligand Y system. And if we wanted to determine the value for Y, we could plot the distribution coefficient against the log of Y. This very much just comes from using the complexation constant and the distribution coefficient. We defined the distribution coefficient on the previous slide. The complexation constant shown here, if this is our equation, or if this is our equation here, this is our chemical reaction. The distribution coefficient is the organic soluble product here, divided by the concentration of metal ion raised to the stoichiometry, times the concentration of ligand raised to the stoichiometry. The distribution coefficient, as we said earlier, is the concentration of the metal ion in the organic phase divided by the concentration of the metal ion in the aqueous phase. And from this equation, it turns out to be the distribution coefficient is just the concentration of the metal X ligand Y complex divided by the concentration of the metal. For this example, we can substitute the KD into the equation for K. We assume that X is equal to 1, and we get a relationship where the complexation constant is equal to the KD divided by the concentration of the ligand to Y, the stoichiometry of the ligand. If we just take the log of the equation, that's the log of K is equal to log of KD minus Y log L. We just rearrange this equation where the distribution coefficient, the log of that value, is equal to log of K plus Y log L. The log of K is constant, since this is a complexation constant, and we wind up getting that the slope of this value is y for the stoichiometry of L. And examples of some distribution coefficients are shown here. The data here is shown for undiluted tributyl phosphate as an extractant, as an organic phase, with nitric acid as the aqueous phase. And then we have some other data that we can compare against, which is diluted tributyl phosphate, 20% tributyl phosphate in dodecane as a function of nitric acid concentration. And here if we're looking at some data for uranium-6, we see that uranium-6 increases up to 6 molar nitric acid. We can also look at some data for plutonium-6. We see the same trend. We see this increase as a function of nitric acid. Start to decrease around 11 molar nitric acid. Again, we start getting competition from the nitric acid itself for coordination with the tributyl phosphate. That lowers the distribution of the plutonium, but for both uranium and plutonium values, their distribution coefficient is between 10 to the first and 10 to the second, so a relatively reasonable value. We can compare that to neptunium-5. We see an increase of neptunium-5 from 1 to 6 molar. However, at 1 molar, it's well under 1. And at 6 molar, it's between 10 to the 0 and 10 to the first. So it's still a relatively low value. And then if we look at values for thorium tetravalent, we see that it also has high distribution coefficient. Again, all the values are greater than 1, as shown here. And thorium is quite competitive with nitric acid, even extracting at relatively high values at high nitric acid concentrations. So one can compare these distribution coefficient values for a system where the data is collected as a function of nitric acid concentration for different metal ions in the system. Again, this point where the distribution coefficient is 1, this shows that 50% would, above this, greater than 50% would extract. Below this line, less than 50% extracts. And we see that trivalents do not extract well. They're all very low values, where tetravalents, the neptunium, thorium 4, plutonium 4 extract well, and the uranium 6 extracts well. And this is up to about 6 molar nitric acid. It shows that in a range between 3 and 6 molar nitric acid, the +4s, +6s are reaching almost a plateau type state for extractions. A number of reaction mechanisms are involved in solvent extraction processes. The first one we'll discuss is solvation extraction mechanism, where we have a charged actinide, a charged ligand with some solvent forming a neutral actinide species coordinated with the solvent. Now within this reaction, the bar shown here that represents the organic phase. So in this system, this starts out in the aqueous phase, this is an organic phase, and the extracted species is the organic phase. Examples of these include extraction with neutral complexes, so the tributyl phosphate, as we've discussed, where this is our functional group, forms a neutral species. The uranyl nitrate coordinates tributyl phosphate. That gets extracted into the organic phase. And I can shift the equilibrium back to a charged species to back extract the uranium from an organic phase into an aqueous phase. Other extraction ligands that can perform this: carbamyl phosphate compounds, which are shown here. And this is our functional group. Metal ions can coordinate over this moiety. CMPO, a phosphine oxide compound. This is the basis for the TRUEX separations for actinides and lanthanides. Again, the metal ion would coordinate at this location. This neutral species very hydrophobic, pulling the complex into the organic phase. And maleimide extraction can replace CMPO for a TRUEX type system. In Europe they call this the Diamex. Again, the metal ion can sit here. The main difference is that the maleimide does not have phosphate. This process is CHON principle, so that these ligands can be degraded at the end of use. Phosphate or sulfur functional groups in a ligand cannot undergo complete degradation. Another extraction mechanisms is similar to solvation. This is ion pair formation. Again, we start with a metal ion in an aqueous phase, a ligand in an aqueous phase, and then a charged ligand with coordinating anion that forms a actinide ligand coordinating anion species in the organic phase. In this system, the charged metal complex with extraction needs to make an extraction with an extractant of an opposite charge. So for instance, a quaternary ammonium salt, positively charged, I need to extract something negative. So I could use a anionic actinide species, aliquat 336, which is also quaternary amine, is a useful extractant. There are also tertiary amines that are shown here. In this case, if you have a monovalent anion, for instance nitrate, chloride, you can coordinate this to form a neutral species with actinide of charge of Z. This may require equilibrium with acid to protonate your extracting organic phases. These resins, ligands can also be sorbed to resin systems. For instance, the Tiva resins uses an amine system which can have nitrate or chlorides. You can pass over a anionically charged actinide species, for instance actinide chlorides, actinide nitrates, which are shown here. So this is again a distribution. It's a K prime value, which is similar to a distribution for a column, and we see we have similar behaviors where we get changes in oxidation states influencing the extraction, where in this case the trivalents are poorly extracted, pentavalents a little bit better, and then the +6s and then primarily +4s in the nitric and HCl systems. Another extraction mechanism is shown here, where you have a liquid cation exchanger and chelating agents. So in this case it's very similar to a metal ion interacting with a ligand, except in this case the ligand happens to be soluble in the organic phase, so it's an organic soluble phase ligand. As we see from this reaction, upon complexation, the proton on the ligand in the organic phase will move into the aqueous phase. So actually measurement of pH, a reduction in pH, would have an indication that the complexation is occurring. So you get the complexation of the formation of the metal ligand phase from the aqueous to the organic phase, and you get ion transfer into this aqueous phase. You need an organic soluble acid, for instance some sort of alkyl phosphonic acids are examples. The one shown here below, thionyl trifluoroacetone, is also a suitable organic acid. As we see, this TTA forms a few different conformations. One, that this enol form, where we could have a deprotonation occur here, that can allow the coordination to occur, and this ligand, the TTA, thionyl trifluoroacetone, uses this trifluoro group here as an electron withdrawing to lower the pKa of this ligand. Something like TTA, we can control the extraction by acidity, and if you look into the literature, the ability to extract metal ions is a function of pH, so you can have a way of achieving separation between metal ions in different oxidation states. Now, these compounds may also have a tendency to form aggregates or micelles, and we'll give an example of aggregate or micelle formation when we discuss third phase in terms of tributyl phosphate. Examples of other organic soluble extracting coordinating ligands are shown here. Similar to thionyl trifluoroacetone as shown in the previous slide, alpha hydroxyisobutyric acid, the compound is shown here, is used in lanthanide separations. It's also was used in the discovery of the trivalent transuranic elements. So for lanthanide separations, the coordination of the lanthanides with alpha hydroxyisobutyric acid allows a size-based separation to occur, since all the lanthanides have the same oxidation state as do the trivalent actinides, particularly americium curium. Another ligand is shown here, HDEHP, or di-2-ethylhexyl phosphoric acid. HDEHP is used in the TALSPEAK system for separating out the trivalent actinides from the lanthanides, and we'll discuss this when we discuss some separations that are specific for americium. And some of the data that's shown here for HDEHP show the distribution coefficient. Again, this is log distribution coefficient as a function of the log of the nitric acid concentration. We see that for uranium, plutonium, neptunium, there's not much of a dependence on the nitric acid concentration on the extraction. Plutonium-4, hexavalent uranium have very good extraction coefficients, all above 10 to the second, while neptunium is pretty poor. It's 10 to the negative, about 1.5. Americium starts out high and goes low as the acid concentration changes, so one could see here that for the neptunium system, one would never have a really strong extraction. For americium, you could tune the extraction based upon the nitric acid concentration. And for, again, separating out uranium from plutonium, one could extract both metal ions into an organic phase and then selectively reduce plutonium to the trivalent state in which it would extract similar to the trivalent americium. So you could have an organic phase that would contain uranium and an aqueous phase that would contain plutonium. The final part of this first lecture on separations will review the PUREX process. An overview of the entire PUREX process is shown here, and we're going to focus in on the chemical component where the separation and a little bit of the purification is concerned. We'll talk a little bit about some engineering aspects of the process, how to achieve these sorts of separations on a larger scale. The PUREX process, which stands for plutonium uranium reduction extraction, is a liquid-liquid extraction process, solvent extraction, and it was developed to recover plutonium. It was developed during the Manhattan Project and patented in 1947. It was deployed at Savannah River in '54 and at Hanford in '56, and it was the workhorse for plutonium recovery at these sites from those dates. In overview of the PUREX process, the uranium and plutonium are extracted from the aqueous phase into an organic phase. The plutonium gets reduced after the separation of that organic phase, and the reduced plutonium then goes back into an aqueous phase while uranium remains in the organic phase, so one would have a stream eventually of just pure plutonium. Some of the processes involved in the overall PUREX process included decladding, some sort of mechanical and chemical decladding step, which would occur here, a nitric acid dissolution step, which includes taking the material, mixing it with a rotary wheel, as shown here, solvent extraction, where the aqueous and organic phases wound up being mixed, as are shown in the separation area, and then a purification step and waste treatment. So the chemical aspects of the PUREX process are based upon this interaction of the dissolved fuel with that aqueous phase with the organic phase. The organic phase winds up being 30% tributyl phosphate in kerosene, and the extraction chemistry is shown here, where we have hexavalent and tetravalent ion extraction. For the uranium, we have uranyl 2+, with 2 nitrates, 2 tributyl phosphates, making an organic moiety. For plutonium, we need to neutralize that, so we need 4 nitric acids, 2 tributyl phosphates, making this neutral moiety. So the uranyl and plutonium are extracted generally from 3 to 6 molar nitric acid. They both have high distribution coefficients, as shown here. The data that was shown earlier for the extraction of metal ions in tributyl phosphate as a function of nitric acid concentration. You see in this experiment, in this range of 3 to 6 molar nitric acid, uranium is high, plutonium is high, neptunium-4 was high, thorium-4 would be high, americium-3 would be low. This is interesting to note for neptunium. One can have different oxidation states of neptunium. As we see the 4 extracts, we would imagine that the 6 would extract. Neptunium-5 doesn't extract very well. And some of the earlier data that we showed is that it has, at the lower end of the 3 molar to 6 molar nitric acid range, as poor extraction. You get higher extraction towards the higher end of this experimental range. So one would have to take care of fixing, or at least controlling or understanding, the neptunium oxidation state during the PUREX process to evaluate its behavior during the separation. Mono, di, and trivalent metal ions have limited extraction. So for this to function, one would need to do the separation and then reduction of the plutonium from the 4 to the 3 drives the plutonium out of the organic phase into the aqueous phase and achieves a separation of uranium from the plutonium. As was stated in the previous slide, the separation of plutonium in the PUREX process is predicated upon its reduction from the tetravalent state in the organic phase to a trivalent state, which then gets removed from the organic phase into the aqueous phase. So in order for this to occur, one has to use some extracting agents. So we see the reason for that is if we go from plutonium-4 with a very high distribution coefficient to something which would be plutonium-3, similar to americium-3, we lose a few orders of magnitude in distribution coefficient, so the concentration of the plutonium in the aqueous phase climbs dramatically. Some of the reducing agents that have been used include ferrous sulfamate. So we start with an iron 2 compound, as shown here. This ferrous sulfamate, the iron 2 gets oxidized to the 3, plutonium gets reduced to the 3. One of the issues with using ferrous sulfamate is that at the end of the day you would have more waste in your system. Since you have this solid iron that you're going to have a hard time getting rid of, it would have to go into the waste form. Here's the sulfamate compound. Another route for performing the reduction is to use uranium-4. The reaction is shown here. Uranium-4 oxidizes to uranium-6, reduces plutonium-4 to plutonium-3. So for every uranium that oxidizes, you get 2 plutonium atoms that reduce. Since you're also performing a separation of uranium, the addition of uranium is not doesn't create a separate waste stream, and it's something that is fairly manageable. Another reducing agent is shown here, hydroxylamine nitrate. The reaction is a little bit more complicated. We have plutonium-4 going to plutonium-3 with nitrate, hydroxylamine nitrate. We form nitrous oxide, water, acid, and nitrates. Again, at the end, the waste here is easily treated, or the reaction is a little bit more complicated. Both hydroxylamine nitrate and the uranium-4 reduction routes are used within the PUREX process. Some of the physical processes that are used for the separations are shown here. Fundamentally, what one wants is a feed where we have an aqueous solution and a solvent. They get mixed. And then, as shown here, the plutonium and uranium would extract into the solvent phase, and the fission products would remain in the aqueous phase. In the laboratory, one could do this with a centrifuge tube, mixing it together on a vortexer, putting it into a centrifuge, separating, and achieving the separation. On an industrial scale, one cannot use that. There are a few processes that are used. One is shown here, a mixer settler, where the aqueous and organic phases are put together in a mixer. They're allowed to travel out. As they travel out of this system, the phases separate. An example is shown here, so we could have an aqueous feed of the uranium, plutonium, and the fission products here. We could have a solvent feed, and the top layer would be pulled out. We could have the loaded solvent would be pulled out, and the bottom layer, which would be the aqueous layer here, would be removed at this end. So we'd get phase separation, and the chemistry would be occurring as the solvent travels along this path. Another route would be a centrifugal contactor, where solvent would be going in, where we'd have a feed going in. They would mix into the contactor. That would be spinning. This would mix and separate. We could pull out the solvent that's loaded. That would come out. The raffinate, or the aqueous phase containing the waste, would also come out at a separate area. So these would be spinning contactors. These contactors are used by the oil industry for separating oil from water. Another route, and we'll discuss this in a little bit more detail, would be a pulsed column, where we could put an aqueous feed at the top of the column. The aqueous is heavier, so it would drop down the column, mixing with the organic phase on the way down. The chemistry would occur, so this uranium, plutonium would be pulled out of the aqueous phase into the organic phase. And then at the very top, we would have an organic layer, which would then be loaded with the solvent, and then we could carry that out to another pulse column to do more chemistry. In the PUREX process, separations are extremely high. For instance, separation of plutonium from uranium is on the order of 10 to the 6th, fission products from plutonium 10 to the 8th, fission products from uranium 10 to the 7th, both with very high recovery of plutonium and uranium. So one of the questions with this is, how does one achieve these high separations, 10 to the 6th to 10 to the 8th, when KD factors are on the order of 10 to the 1st or 10 to the 2nd? The answer is multiple stages. And from the previous slide where we talked about the different methods, the contactors, the pulse columns, one could imagine having a system where you would achieve a separation. So you'd start off with fresh organic solvent. It would go into one pulse column. It would come out and go into another pulse column, and then another, and then another, and keep going until you would have a solvent that would be fully loaded. The feed would be going countercurrent in the opposite direction. So over here you would have unloaded solvent. Over here you'd have loaded solvent. You'd have loaded feed and unloaded feed. So you can achieve each one of these separations from the chemistry would be on the order of 10 to the 2nd, but having many steps, you can get the separations on these orders. That's how the process is used, and that's where the engineering comes in to achieve these very remarkable separations. An example of a pulse column separation is given here. The organic phase is 30% tributyl phosphate and kerosene. The aqueous phase is 3.5 molar nitric acid, and the strip phase contains 1.5 molar hydroxylamine nitrate in the aqueous phase of 3.5 molar nitric acid. So within the pulse column, the dissolved spent fuel is in a hold tank and then added to the extraction column. The extraction column is the 30% tributyl phosphate and nitric acid, and as a drop is added, it makes its way down the column. Since it's the aqueous phase, it accumulates at the bottom of the column. From this point, the chemistry occurs where the uranium and plutonium is extracted into the organic phase. This extraction column can be fed into another column, another extraction column, and another extraction column in a countercurrent method as discussed previously. After the extraction column, the organic phase is transferred to the bottom of the scrub column. The scrub column being 3.5 molar nitric acid. The organic phase makes its way up the scrub column. Under these conditions, 3.5 molar nitric acid, the uranium and plutonium remain in the organic phase, and any residual trivalent, divalent, or monovalent metal ions are extracted out. This scrub, you can have many more of these scrub columns feeding in a countercurrent method. This allows us to get to the 10 to the 6th to 10 to the 8th purifications. And then the organic phase is added to a strip column. It's put on the bottom of the strip column. Moving up, the strip column contains the 0.1 molar hydroxylamine nitrate. And the organic phase, as it moves its way up, the plutonium is reduced and moves into the aqueous phase. And at this point, we have an organic phase that contains the uranium, a aqueous phase that contains the plutonium, and again, you can have countercurrent strip columns. We'll end this discussion on solvent extraction PUREX process talking about third phase formation. In liquid-liquid solvent extraction, certain conditions can cause the organic phase to split. For instance, we'll give examples for PUREX type conditions in tributyl phosphate. It's also possible with other advanced separations. One term that's used to define where the split occurs is the limiting organic concentration. It's the highest metal, for instance, the highest metal content in a phase prior to the split. The organic phase will split into a light phase, which is mainly diluent, and a heavy phase, which is the extractant, and it's metal rich. For a process that involves the separation of a fissile material, such as plutonium, you can imagine that this would have safety issues, particularly with criticality. There's also interest in using this third phase formation, which appears to be micelle formation, to be exploited for synthesis of actinide components. Here are some pictures of third phase formation. So you see this is uranium, the aqueous phase, an organic phase where you can certainly see a light phase, and then a heavy uranium-rich phase. We see the same thing for plutonium-4, plutonium-6, neptunium-4, and neptunium-6. Here's the data showing some limiting organic concentration of actinide ions in a 7 molar nitric acid, 1.1 molar tributyl phosphate in dodecane at 20 to 25 degrees. What's shown here, there's a trend for tetravalent metal ions, that as we go from uranium to plutonium, the limiting organic concentration increases, while for the hexavalent metal ions, under these conditions, uranium does not form a third phase, neptunium does, and plutonium forms it the easiest. And here's an example of some boundary conditions for limiting organic metal ion concentration for neptunium, tetravalent neptunium, as a function of nitric acid concentration. This also shows the concentration of the acid in the organic phase, and we have the same data here for neptunium-6 and the concentration of the acid in the organic phase. This completes part 1 of the lecture on separations. Part 1 covered solvent extraction with the PUREX process highlighted. The second lecture on separations will review ion exchange methods and volatility-based separations. Please continue with part 2.